When we talk end behavior, what we're talking about is what's happening to a function as x, which with our profit, revenue, cost functions has represented production level. So what happens as our production level gets increasingly large? In terms of applications, this can allow us to investigate things like average cost over time. So we've already looked at an example with average profit with a production level of 25 units. Now what we can do is investigate what's going to happen to our average value, say average cost, average profit, etc., as our production value just grows and grows. So in this case, in example 6, we have a company is planning to manufacture snowboards. The fixed costs are $100 per day, and the total costs are $5,900. We want to assume that the total cost and output per day are linearly related, and we want to come up with an equation for our cost function. So this means we want to generate a function of the form c of x equals mx plus b, since we know we have a linear relationship. Our total cost is $5,900 at a production level of 20 boards, and we had fixed costs of 100. So solving for m, we would get 290, which gives us a cost function of 290x plus 100. From there, we want to find the average cost function, so c bar of x, which is just c of x over x, or 290x plus 100 over x, which again we could also rewrite as 290 plus 100 over x if we broke that up into two separate fractions and reduced. In part C then, we want to find the limit of the average cost function as x approaches infinity, and then interpret that result. So what that means is we want to find the limit as x approaches infinity of this average cost function, and we can use that in either form. And then using the techniques we talked about in the last video, we could plug that into Wolfram Alpha to generate a result of 290. So since we're talking about applications, we care about interpretation. So we want to add some interpretation and talk about what this result tells us. So this tells us that over time, or as production increases, our average cost per board will be approaching $290. So as our production level continues to increase, we have this anticipated cost, average cost per unit that we'll be approaching. So that's a situation where we're considering just a single product. We could also use this idea of average cost over time, or end behavior, to look at comparing two different products. So in this case, we have two different models of appliances, an energy efficient and a conventional model. We want to compare the average cost of these functions over time to determine which one is going to be the better purchase. So in part A, we want to use the information in the table above to construct a total cost function for the energy efficient model, so the information in this first column, and then find the average cost function. So in this case, we're given two different values, a fixed cost, which is the $800, that initial purchase price, which is going to be our value for B here, the fixed cost in our linear cost model. And then we have an annual cost to operate, which would be our variable cost, because that will change depending on how many years we run the appliance. So that would be our variable cost times the years, making our cost function 54x plus 800. And then would mean that our average cost function for the energy efficient model would be 54x plus 800 over X. Then we want to do exactly the same thing for our conventional model. Again, we would look back up at the table. We have a fixed cost, which is that initial purchase price, so that initial cost of the appliance, and then the variable cost, which is the cost to operate it per year, giving us a cost function of 69x plus 740. From there, we can generate the average cost function, which would be 69x plus 740 over x. So for these two different models of appliance, we have an average cost function. In the last piece of the problem, we want to find the limit of each of those average cost functions as x approaches infinity, and then interpret that result. So again, using the techniques from the last video, we could find the limit of this function, the average cost function for the energy efficient model, as x approaches infinity, and we would get 54. We could also take the limit as x goes to infinity of the average cost function for that conventional model, and in this case we would get 69. And then, again, since we're talking about applications, we want to talk about interpreting that result. So we can compare these two average cost functions over time, which would tell us that over time, the average cost per year will be less for the energy efficient model. So even though the energy efficient model had a slightly higher initial cost, over time, the average cost to operate that per year will approach $54 versus $69 a year for the conventional model. Or the other way to say that would be that the energy efficient model is, over time, the better value.